In this lecture, we will be covering the topic of derivatives of parametric curves. Recall the definition that a parametric curve C in the xy plane is a pair of functions x equals f of t and y equals g of t that give x and y as continuous functions of the parameter t. We call f and g parametric equations. A natural way to think of this is when the parameter t is time, and the parametric equations give you the xy coordinates of a particle moving through the xy plane in time. So say at time 0, we're here, and as you run the clock, the parametric equations give you the trajectory of where the particle is at different times. In the case where the parametric equations x equals f of t and y equals g of t are smooth, and by that we mean f prime of t and g prime of t are continuous functions and never simultaneously zero. We have to outlaw the simultaneously zero part, because if f prime of t and g prime of t are both zero, that means the particle's x-coordinate is not changing and the particle's y-coordinate is not changing. So that means as you run the clock, you hit a point in time, the particle stops. So we have dy dx, which is our derivative of y with respect to x, the derivative that we're used to working with from our studies of differential calculus up to this point, can be written as dy dt divided by dx dt for any t such that dx dt is non-zero, so we don't have division by 0. And the way that we derive this is quick. It's a quick application of chain rule. We know that dy dt by the chain rule is dy dx times dx dt, and we see here that if we solve for dy dx, we obtain this formula 1 here. So let's take a look at how we actually use this. So consider the parametric curve given here. X equals t cubed minus 4, y is 2t squared plus 1, and the parameter t can be any real number. And we want to find dy dx. And we will use that formula that dy dx is dy dt divided by dx dt. So we need to find these two derivatives. So first we have dx dt, differentiating the first parametric equation with respect to t gives us 3t squared. Differentiating the second parametric equation with respect to t gives us dy dt is 4t. And then we can apply our result here to say that dy dx is dy dt, which is 4t, over dx dt, which is 3t squared, and we get 4 over 3t. And the idea now is the derivative of y with respect to x can be calculated in its own parametric way here, because it depends on the parameter t. So at any given time, you can plug that in here and you get the derivative of the curve. We can also look at the second derivative of parametric curves. So if the parametric curve given by x equals f of t and y equals g of t has continuous second order derivatives, f double prime and g of double prime, that are never simultaneously zero, then we have this result here, d squared y dx squared, which is the second derivative of y with respect to x, or the derivative of y prime with respect to x, can be written as the derivative of y prime with respect to t over dx dt. And the way that we can do this is with chain rule yet again. So if we want dy prime dt, then that can be written as dy prime dx times dx dt by the chain rule. And again, as we did before, if we solve for this term, which is the second derivative that we're after, we get dy prime dt divided by dx dt. And we can use that in the example we just worked through. So we said that d squared y dx squared is dy prime dt divided by dx dt. This is what we're calling y prime, which is the part we solved for in the first examination of this example. So we need the derivative of this with respect to t. So we think of this as 4/3 t to the minus 1. So dy prime dt can be written as minus 4/3 t to the minus 2, or minus 4 over 3t squared. dx dt was 3t squared, differentiating this parametric equation with respect to t, and now applying this formula gives us d squared y dx squared as dy prime dt, which is minus 4 over 3t squared divided by dx dt, or 3t squared, which gives us minus 4 over 9t to the fourth. And so now we have the second derivative of y with respect to x as a function of the parameter t. And it's important to recognize these are not formulas that you really have to memorize, because you can get them from this one step of the chain rule. One final example is a famous example called the spiral of Archimedes. R equals a theta for some positive a, and theta greater than or equal to 0, and this is a polar equation. But we can think of a polar equation as having parameter theta. The parameter doesn't necessarily have to be time. It can represent anything. And here we can also think of theta as representing time, which we'll see in the next slide how it makes sense. But we want to calculate dy dx in this context. So first, by chain rule, we know dy d theta can be written as dy dx times dx d theta. And thus, solving for dy dx gives dy dx equals dy d theta over dx d theta. Now recall from polar coordinates, we know that x equals r times cosine of theta, and y is r times sine of theta. But from our equation here, r is a times theta. So we can replace r with a theta in each of these equations. This allows us to calculate the derivatives in the right-hand part of this expression. First, dx d theta, using the product rule, will be the first, a theta, times the derivative of the second, with respect to theta, which is negative sine of theta, plus the second, cosine of theta, times the derivative of the first, which is a. dy d theta, differentiating this with respect to theta, with product rule, we have the first times the derivative of the second, which is cosine of theta, plus the second, sine of theta, times the derivative of the first. And these two things can now be plugged in here to get dy dx equals, the numerator is dy d theta. We see we can factor an a out. We have a times theta times cosine theta plus sine of theta divided by dx d theta, which we can also factor out in a, and we get negative theta times sine of theta plus cosine of theta, and we see that the a's in fact cancel. And we now have the derivative of y with respect to x here as a function of the parameter theta. This is what the graph looks like, so you see why it's called the spiral of Archimedes. And the idea is, think about theta being time, and when you start the clock at 0, remember a is positive, so as the time increases, r, which is the distance from the origin, is increasing linearly in time, and so as you run the clock, the point is just getting further and further away. And what we just calculated would be at any given point, we get the slope of this tangent line, dy dx. And so we see that chain rule is very effective in being able to calculate derivatives of parametric curves.